Okay, we're going to be graphing quadratic functions. And this one's going to be in the form, this is the basic, f of x equals ax squared. So some things we need to first understand is some vocabulary. Quadratic function in standard form. Okay, well, that would be in the form of f of x equals ax squared plus bx plus c. And like I said today, we're just graphing this first part, the ax squared part. The bx and c we're not graphing. Okay, and the graph we're going to come up with is a parabola, and a parabola is kind of like this happy face looking graph. It's a U-shaped, either up, down, or down, maybe a sad face. Okay, and the point at which is at either the maximum or minimum is called our vertex. So when you're looking at a parabola, the vertex is the maximum or minimum point. That is our vertex. Okay, so either there or, that's really not a great picture to show a vertex on, or there. Okay, those would be our, that would be our vertex. Now an axis, whoa, excuse me there. Okay, an axis of symmetry, whenever you graph a parabola is a mirror of itself right down the middle. So if you draw a line kind of down the middle of your parabola, I'm having a hard time not switching over there. Okay, let's try this again. So, got this parabola, and right down the middle we have this line, and that line is called the axis of symmetry. Now symmetry, or something symmetrical, it's the same on both sides. So like this point right here would be a reflection over the axis of symmetry of that point right there. And we're going to see that in our graphs. But this line right here is called our axis of symmetry. And it's always in the form of x equals something. Okay? So I have some vocab that we can use. And we're going to do that when we graph the parent function. Now the parent function of f of x equals ax squared is just when a is 1. So in other words, we have 1x squared. We have this right here. And notice, I don't have any b or c terms. Okay? And anytime I'm without a b term, let me say that, anytime you're without a b term, then you always start your table when x is 0. And I'm always going to put 0 right in the middle because that is going to give me my vertex. So make a note to yourself. You always start right here. You always start with your vertex at x equals 0 when you don't have a b term. Whenever you are without a b term, start the vertex at, or start the table, excuse me, x equals 0 for the vertex. Okay? You have to have a starting place because that's going to give you your curve. And I put it right in the middle because it's going to be my vertex. It's going to be the curve point of my graph. Okay, so if I'm going to fill out this table, notice I have my input, I have my output, and in the middle is my rule. My rule is the right-hand side of the equation, the x squared. So I'm going to input 0 into my rule. I'm going to input it for x. Well, 0 squared is 0. That gives me an ordered pair, 0, 0. And that ordered pair is right here, which means that is the vertex of my graph. The vertex of my graph is going to be 0, 0. I promise it's the vertex. Now, I haven't explained exactly why it hasn't moved, but as we start progressing in our graphs, you're going to see it's always the vertex, and then when we start graphing ax squared plus bx and plus c, and we deal with the b and the c, you're going to see why it's always at 0, 0. Okay? For now, just accept whenever you are without a b term, start the table at x equals 0 for the vertex. Okay, and what that allows you to do is allows you to just build your table. So after 0 is 1, so I'm just going to put in 1 for x. And 1 squared is 1, so I get the ordered pair 1, 1. So let's keep that a little cleaner here. So 1, 1. Okay, so I could keep putting in values for x, right? Okay. So I put 2 in. 2 squared is 4. So I get 2, 4. Okay, I put -1 in because it becomes 4, 0. -1 times -1 is +1. So I get -1, +1. And I put -2 in, and -2 times -2 is, yeah, it's +4. So I get -2, +4. And so when you start graphing these, you'll notice, well, 1, 1 is right here. 2, 4 is right here. And then -1, 1 is actually right across. It's right there. And -2, 4, well, it's actually across from 2, 4. And what you have is you have this graph that you want to be a little cup shape at the end. So make sure you get that cup shape there. Okay. Don't make it a V shape. So I like to kind of draw the U first and then hit the other points. Okay. Same thing here. Hit that point. Do a better job at hitting that point than I did there. Okay, there we go. That is our graph. That's our parabola. And notice the vertex was 0, 0, but my axis of symmetry, that's this line right here. It's the line of reflection right down the middle. It goes through the vertex. And that line is at x equals, well, what does x equal at that line? It's, well, x equals 0. That is my axis of symmetry. And what does that do? That means if I take this point, I can reflect it over to here. This point, I can reflect it over here. In fact, if I know what 3 is, if I were to put 3 in for x, so I get 3 times 3, which would be 9, right? Really, I'm just doing my perfect squares, but if I know what 3 is and I continue my graph up, I can find -3 just by moving this point over across the line. Move it, it's a reflection. Okay, that is my parent function. And really note what you're doing. X is 1, we get 1, 2, 4, 3, 9. 1 squared, 2 squared, 3 squared. The next one would be 4 squared, which would be 16. That's the parent function. Okay? Let's fill out the rest of these characteristics. Okay? We have vertex and axis symmetry, but the domain. In other words, where does it exist on the x-axis? Are there any inputs for x that would be undefined if you put them in? Is there any way you can put a value in for x and get like a no solution or undefined? And there's not. You can put 1,000,000 in or -1 million and you get an answer out. You get an output. So the domain is all real numbers. Okay, and we're going to abbreviate it, or I'm going to abbreviate it with this symbol right there, all real numbers. And the range, well, the range starts here at 0 on the y-axis, and it goes up. My lowest point is 0, and my graph is moving upwards. So my range is y is always bigger than or equal to 0. When is my function decreasing? Well, that's a little more difficult. So what you have to start to do is you have to start looking at your graph, and actually let me use a highlighter here. And you're going to say, okay, if I was on this graph walking, let me read it from left to right. On this side, as I approach the bottom, I am declining. I am decreasing. So really, I measure increasing and decreasing on the x-axis. So until I get to this point on the x-axis, I am decreasing. So I am decreasing all on this side, okay, of my axis of symmetry, right? I am decreasing on that side of the axis of symmetry. Well, the axis of symmetry is at x equals 0. So I'm decreasing over there. And on the other side, I'm increasing. So really what I need to look at is over here, I'm decreasing. My graph is decreasing. And on this side, I am increasing. Okay, when x is less than 0, all these values that are less than 0 on the x-axis, I'm decreasing. When x was bigger than 0, I'm increasing. When x actually equals 0, well, notice I'm at 0. Nothing's happening. I'm at a level ground. Okay, I'm at the bottom. That's how we deal with that. Okay, now we spent like 10 minutes on that. So let's kind of pick it up and try to see what A does. So what we're going to do is kind of look at how A affects our graph. So if you think of your parent function, we're going to graph a different graph. We're just going to put a negative in front of our parent function and see how it changes it. So my rule now is negative x squared. And how is that going to compare to x squared? Well, we already know x squared, right? It was our last graph. It's where we had 0, 0, 1, 1, 2, 4, and 3, 9. And then we had the reflected points. They went right across here, right? That's the same thing. That is the one we just graphed right here. Okay, now I'm not going to connect the points. I'm just going to put the points. Okay, now let me switch up colors here. We'll call this in that color, okay? And we'll move here. Okay, so negative x squared. That's going to be this one. Okay, and like I said, previous statement, whenever you are without a b term, start at x equals 0 for your vertex. So I'm going to put the vertex in the middle. X is 0. I have negative 0 squared, which gives me 0. Now notice what I did there, and I just did it really fast. I just inputted a 0 in those parentheses. Well, this negative stays negative for all my work. And this squared stays squared for all of my work. The only thing that's changing is the x. And we're going to substitute that inside parentheses. Okay, so I have 0. I'm going to put 1 in. 1 squared is 1. Times negative is negative 1. I'm going to put 2 in. 2 squared is 4. Times negative 1 is negative 4. I'm going to put negative 1 in. Negative 1 squared is 1. Times negative 1 is negative 1. I'm going to put negative 2 in. Negative 2 squared is 4 times negative is negative 4. And so I have these points. I have negative 2, negative 4. I have negative 1, negative 1. I have 1, negative 1. And I have 2, negative 4. Okay, and so you start graphing them. Well, 0, 0 is the same. 1, negative 1. 2, negative 4. Negative 1, negative 1, and negative 2, negative 4. And if I wanted to put 3 in, I'd actually find that that was negative 9. And negative 3 would give me negative 9. Okay? And so you see this graph form, and really, this graph looks just like it's been turned over, right? Like, if you were to turn your screen over, you would see the parent function just opening downward. And that's what a negative does if you remember your transformations. Okay? When you compare it, it's a reflection over the x-axis. Okay? When we compare it to x squared, this is just a reflection over the x-axis. So what you need to take away, when you have a negative, your graph opens down. So when A is negative, the graph opens down. And when A is positive, it obviously opens up. One way you can think about it, hey, negative is a frowny face, right? Positive is a happy face. Okay. Now it's kind of childish, but you know, that's the way it goes. Okay, the vertex, well, the vertex is 0, 0. Axis of symmetry is still right here. In fact, we didn't even have to fill out the whole top part of this table. We know it's going to reflect, but it's at x equals 0 again. The domain, still all real numbers. Range, well, it starts at 0 on the y-axis right here, but it doesn't go up, it goes down, so it's less than or equal to 0 now. Then we start talking about the increasing, decreasing thing, right? So once again, let's go until we get to that axis of symmetry. Our graph over here, remember we always start on the right or the left-hand side. We read left to right. Okay? And so over here, my graph, if I was on this graph, oops, if I was on this graph, I'd be moving up the graph, right? I'd be increasing. I'd be going uphill. So my function is increasing until x is at 0. So when x is less than 0, my function is increasing over here. It's decreasing over here, and that's when x is bigger than 0. Okay, so it kind of flipped around there. All right, so one rule we just figured out there. That's one thing A does. All right, let's take a look at another one. Now a is greater than 1, so we have 2.5x squared. So once again, I'm going to go ahead and take my parent function. I'm going to put it on here. Remember, that's just the 1, 1, the 2, 4, and the 3, 9. Okay, and its reflections. And so I've dealt with that. I'm now going to graph the 2.5x squared. So my rule, 2.5x squared, which means I have 2.5 and I have a squared on all of these. The only thing that is going to change in my table is I'm going to input an x in those parentheses. And we're going to keep changing x, right? We're going to give different values. And we always start at, 0, as long as there's not a b term. So 0 squared is 0 times 2.5 is 0. We have 0, 0. Oh, there we go. So it's 0, 0. Put in 1. Okay, 1 squared is 1 times 2.5 is 2.5. So we get 1, 2.5. Notice this point moved up a lot. Okay, and we now have 2. 2 squared is 4, and 4 2.5s, well, that's like 4 quarters almost. That's 10. Okay, well, that brings me way up here. So this point that was right here has really moved up. Okay, well, I'm going to reflect those points this time. Rather than just figuring it out, like putting in -1 and -2 and doing all the math behind it, I'm just going to reflect it. I know this is going to be 2.5 because it's a reflection of this point. And I know this next one's going to be 10 because it's a reflection of that point. Now you could do the math just to double check. But notice when I actually connect these points here, and be careful when it gets really skinny like this, that it doesn't look like a V. But when I connect the point, it looks like my graph kind of went on a diet, right? It thinned out. And really, we call that thinning a stretch. This point has stretched. It's moved from here at 1 all the way to 2.5. It's like we multiplied 1 by 2.5 to get to 2.5. And this point that was at 4 moved all the way up to 10. Well, 4 times 2.5 is actually 10. It's stretched. It's moved upward by a factor of 2.5, which kind of makes sense because the parent function is x squared, and we're multiplying the x squared by 2.5. So this is called a vertical stretch by a factor of 2.5. By a factor of, by the way, we're going to abbreviate for now on as BAFO. B-A-F-O, 2.5. Okay, we know our vertex, it's at 0, 0. We know our axis of symmetry is actually at x, oops, no parenthesis on that, x equals, well, it's right here again, still at x equals 0. Okay, that's our axis. Our domain is still all real numbers. Our range, it's opening up and it starts at 0, so it's y is greater than or equal to 0. It's increasing. Well, let's go ahead and highlight it again. We're over. Whoa, that is red. Let's go back to yellow there. Okay. Well, if I go to my axis of symmetry right there, there it is. And notice on this side, when I'm to the left-hand side of the axis of symmetry, I am right now decreasing. And over here I am increasing. Pretend you're walking on the graph. So when x is less than 0, I'm decreasing. When x is greater than 0, over here, I'm increasing. All right. Well, we did when a was greater than 1. Let's do when a is between 1 and 0. So it's less than 1, but greater than 0. We know what happens when it's negative. It flips it upside down. So if we put our parent function back on there, okay, so our x squared, once again, we have 0, 1, 1, 2, 4, 3, 9. Okay. And then I move on and I take my 1/4 x squared. So I'm going to write my fourth like that. I'm not a big fan of doing that, but it's the only way I'm going to really fit it. Once again, I always start at 0 because there's not a b term, okay, until I get a b term. So I have 1/4 and 1/4 and 1/4, and notice I keep leaving the x out because that's what I'm going to put my value of x in. So that is 0. Gives me the ordered pair 0, 0. So my vertex is at 0, 0. Which, by the way, if your vertex is 0, 0, your axis symmetry is also your x value of your vertex. It's at x equals 0. So you kind of kill two birds with one stone when you find this point right here. It's axis symmetry and the vertex, just so you know. Okay. Well, now, usually we're going up by 1, but since I have a fraction and it's an even number, I'm going to go up by 2. Because I put 1 in here, I'm just going to get a quarter out, and it's like way over here, right? I'm going to put 2 in, okay? When I do that, that's 2 squared, which is 4, times 1/4 is 1. So I get 2, 1. So notice this point has moved from here down to there. I'm going to put 4 in. I'm going to go up by evens now. I could use 1, okay, but when I put 4 in, 4 squared is 16 times 1/4 is, yeah, it's 4. Whoa. Okay, so that is right there. Well, my other point would have been way up there. Now, I'm going to reflect those points, so if I have -2, the same distance away, it's going to be 1, and -4 is going to be 4. Notice my graph has kind of got a little bit wider. Okay, this point right here has moved down. It's like we're multiplying this point by 4 to get to here, or taking this point and dividing by 4. And like I said, this would have been 1/4, so it would have been 1 divided by 4. This is called a vertical. It's shrinking vertically. It's a vertical shrink. That means it's shrinking towards the x-axis by, and let's use BAFO here, by a factor of 1/4. Okay, vertical shrink by a factor of 1/4. All right, which makes sense because you're taking x squared and you're only taking 1/4 of it. So you don't even get the 1, you get 1/4. You don't get 4, you get 1/4 of that, which is 1. You don't get 9, you get 9/4, or a 2 1/4, which would actually be like right around here. It'd be a little closer there. Okay. All right. Our domain, all real numbers still. Range, y is still opening up, so greater than or equal to 0. It's increasing and decreasing. Hopefully you're kind of getting in the habit of seeing that, but boy, oh boy. Gotta switch my highlighter again. Don't want that. There we go. Okay. So if we go all the way to our axis of symmetry, okay, this is when on this side, on the left-hand side of the axis, at least right now, we have x is less than 0 over here. And on this side, we have x is greater than 0, right? Because here's 0. And over here, we're going down. We're decreasing. And over here, we are increasing. So where are we decreasing? Well, x is less than 0. We're decreasing and x is less than 0, and we're increasing. We're going uphill, okay, when x is greater than 0. All right. Well, notice this graph got wider. This graph got narrower. X was bigger than 1, or a was bigger than 1, and a is less than 1 but greater than 0. So one note to make to yourself, another thing a does, a is like an accelerator. Okay, so let me switch some colors here. A is like an accelerator. A tells you how fast your graph is moving upwards. Okay? A tells you how fast the graph moves up, or I guess moves up or down. Okay. So if A is greater than 1, it's like going really fast. It's stretching. When A is between 0, excuse me, not X, this should be A. Between 0 and 1, you get a shrink. Okay, it goes really slow, so you can kind of think wide. It's a wide graph. Here you can think narrow. It's a narrow graph. Okay? So that kind of gives you an idea. So when you're looking at a graph, I'm this last graph here. By the way, this is our last graph. Okay? I can think, okay, well, I have my parent function. Okay? Right here of x squared, so just like we've done, 1, 1, 2, 4, 3, 9, and then reflect it. Right? And then I'm thinking, well, I have negative 2x squared, so that's my rule. Well, the 2, I know what the negative does. The negative reflects, it's a reflection, over the x-axis. Okay? That's what we did back on this slide, right? It's a reflection over the x-axis. Well, what does the 2 do? Well, the 2 is actually greater than 1, right? Okay? So the 2, in this case, is going to be a vertical stretch over, by a factor of 2. What I like to think is the further A gets away from 0, the quicker my graph moves to infinity, up or down. The narrower it gets. The further I move away from 0, the narrower my graph gets. The closer I get to 0, the wider it gets. It gets really, really wide if you're really, really close to 0. Okay? So that's another thing you could write down. The further A is from 0, the narrower the graph. The closer it is to 0, the wider the graph. Okay? I'm not going to write all that out, but I'll let you write it out. You can pause and do that. But notice I don't have a B term, right? So I'm going to start at 0. It's my vertex. I have negative 2 times 0 squared. Gives me 0. So I get 0, 0. I put in 1. I get negative 2 times 1 squared, which gives me, well, negative 2. So I get 1, negative 2. And I put in 2. I get negative 2 times 2 squared, which is 4 times negative 2, or negative 8. So I get 2, negative 8. So now down here, I can reflect those points. So that moves to there. This one moves to there. I can draw in. Ooh, that was a bad point right there. Let's try that again. There we go. And that is not a great curve. Let's try. There we go. All right. And you know, I can keep filling in my table if you need to. Unless your teacher gets you a hard time, or you're trying to make predictions, and you really don't have to keep filling in the table. Okay. So this is my stretch. Notice this point was 1 away. It's now 2 away. We move it down, we reflect over the x, and then we double it. This point was 4 away from the x-axis. Well, we reflect it down to negative 4, and then we double that. It's now 8 away. That's what we're doing here. My vertex is still at 0, 0. My axis of symmetry is still right here. Right? It's at x equals 0. My domain, still all real numbers. My range, it's opening down, so it's less than or equal to 0. Y is less than or equal to 0. My function, well, let's go ahead and, again, take our highlighter on this side of the axis of symmetry. Over here, this is where over here x is less than 0, and I would be increasing on my graph. Over here, x is greater than 0, and I'm actually going downward, so I'm decreasing on my graph. So when is it decreasing? Well, that's when x is greater than 0. When is it increasing? Well, x is less than 0. All right. Yep, that's all I got for you.